Parece que ela queria ir. Quando depois passamos para o Hélio, alguns brasileiros até que gostam disso. Pouca cadeira.
A semana que vem a gente tenta
é para ter
Boa tarde a todos. Bom, é uma grande satisfação receber aqui no Departamento de Física o professor Bellini, do Instituto Nacional de Ottica de Florença. Então, antes de passar a palavra para Catiúcia, que vai apresentá-lo, vocês devem ter notado um corpo estranho aqui no meio do auditório, né? Então,
não fui eu que levantei aqui.
Isso aí é estranho mesmo.
A gente está, aos pouquinhos, tentando fazer com que os nossos colóquios sejam transmitidos via internet, ao vivo, inclusive a pedido de vários dos ex-estudantes nossos, que estão aí espalhados pelo mundo e pelo Brasil, que sentem saudade dos nossos colóquios e gostariam muito de assistir, de voltar a assistir alguns ao vivo. Então, o colóquio do Marco Bellini inaugura essa tentativa. Pela lei de Murphy, não vai funcionar 100%, a gente já viu aqui, tá certo? Qual era o nosso objetivo? Nosso objetivo era fazer com que houvesse uma imagem aberta do palestrante e também uma espécie de inset na tela com o PowerPoint projetado, ou seja, para que a pessoa possa ter uma visão geral da palestra e também ler os detalhes do que está sendo projetado na tela na forma de um inset. A gente estava funcionando tudo bem até 15 minutos antes, então o inset não vai ser possível dessa vez. Quem sabe na semana que vem a gente melhora, tá bom? Então fiquem atentos. Eu vou passar a palavra para a Catiúcia para apresentar o Marco, por favor.
Thank you all for coming. Marco Bellini, he did his PhD, he finished the PhD in 1995. It was on the topic of high-resolution spectroscopy of atoms and molecules. Then later, as a young researcher, he had a collaboration with Ted Hench, which resulted in a nice work that was fundamental for the development of the frequency scopes. And for that, the Ted Hench then won the Nobel Prize in 2009. And now, as a senior researcher, he leads two groups in Florence, in the University of Florence. One group in ultrafast optics, the generation of high-order harmonics, and the other group is in quantum optics. So you're going to hear the nice research he has been doing the last years today. But let me just mention that this is the second time Marco is visiting us here in Recife. He's coming under this collaboration program that we have that is funded in by CNPq, Ciência Sem Fronteiras, of course. And so, more specifically, this collaboration is between his group and our group in Brazil, involving Professor Daniel Filippo, Lucio Scioli, and myself. And okay, so I think I more or less finished this introduction here while we have still sun. The city is not flooded, and so Thank you, Marco, and I hope this time the talk will really go through.
Okay, so first of all I want to thank the organizers, everybody being here.
Would you like to use the microphone?
Do you think I need the microphone?
Yes.
Okay. Does it work? No. Okay. Can you hear me? Okay, so I want to again thank the organizers for inviting me here. I'm very honored to be here for this colloquium. I hope it will not start raining again today. And okay, I'm going to tell you something about our activity in Florence with extreme light. Call it extreme because we have been doing many different things in the last few years in very different regimes. And as Katusha said, I started with, I did my undergraduate and PhD thesis on high resolution spectroscopy with far infrared, which means that we were using something like very monochromatic sources, which had coherence times, let's say, of the order of milliseconds, so very narrow line widths, and very low intensities, because we were working in this region, which is now called terahertz region, and where it was difficult to generate radiation. And again, we were using very long wavelengths. Then at the end of my PhD, I switched to something else, something completely different. So it was an extremely different regime. And I started to work with high order harmonics in extreme ultraviolet. So in this case, instead of using very monochromatic sources, I started to work with extremely short pulses in the range of femtosecond durations. Instead of using very low intensities, we started to use intensities of the order of 10 to 15 watts per square centimeters. And we passed from one extreme of the spectrum, far infrared, to the other extreme ultraviolet. So that was an extreme change. And I'm going to show you more of these extreme changes, and I hope to convince you in the end that changing so much in the end is not so bad, because you can take some ideas from one field to another and maybe learn something new. Okay, well, the difference between pulsed and continuous wave light that I used to work with. So with continuous wave lasers that we normally use for high spectral resolution, high resolution spectroscopy, you have a very well-defined frequency, of course. So you have very narrow line widths, then long interaction times with matter, and it's of course good for spectroscopy where you want to resolve in a very fine way, let's say, transitions, atomic or molecular transitions, and so on. So it's good for frequency resolved investigation. On the other hand, if you have a pulse laser, which is what I moved to at some point, you have a very well-defined timing, because we have very short pulses, which can be just a few, let's say, oscillations of the electromagnetic field. And so you can concentrate, for example, all the energy in these very short pulses, so you can have very high intensity interaction with matter. And it's very good, of course, for time-resolved studies, so you can measure something that happens in very short time scale, but it's very bad for spectroscopy, because you have huge bandwidths, and so it's difficult to measure frequencies accurately with these short pulses. So, but okay, you can use these pulses, for example, for having high-intensity interaction with matter, and to drive the highly nonlinear phenomena. So the phenomena that I started to work with when I finished my PhD was high-order harmonic generation. And so this is what happens whenever you have an intense pulse laser and you focus essentially anywhere. You can have, let's say, harmonics. So you start from the infrared, you can easily get, if you focus in air, the third harmonic. And okay, in air you can just have that one, because higher harmonics with shorter wavelengths are absorbed. But if you do it in a gas jet, you can produce higher order harmonics. And this is because the electric field of the laser can be so intense that it's incomparable to electric field which keeps an electron bound to the nucleus in an atom. So when you have such high fields, high laser fields, then you can start to have very, say, strong interaction with the atoms and highly nonlinear effects. And a simple model to explain what happens when you shine one of these very short and intense pulses on an atom is this three-step model which comes from Colóquio in Canada. And you can model it this way. I mean, the electric field of the laser is so strong that it bends the potential of the atom so that electrons which are initially bound to the atom can tunnel out this potential barrier and can be freed in the continuum, can get, let's say, accelerated by the laser field. And since the laser field changes sign every optical cycle, at some point they can be driven back to the nucleus and recombine. And when they recombine, they can, let's say, release all the kinetic energy that they have acquired by oscillating the field, plus the ionization energy. And so they can release photons of high energy. So you can produce diode harmonics in a simple way by shining an intense pulse in a jet of the gas jet. Usually we use noble gas atoms. And what you get at the output are all the harmonics of the fundamental field. So we start from the infrared that you can get to the extreme ultraviolet or near soft X-rays. This is a typical spectrum, behavior of the spectrum of high-order harmonics. At the beginning you have the intensity of the successive harmonic orders goes down exponentially, and then you have the region which is called plateau, which can extend for quite a lot. And the extension of this plateau is given by this formula, which is ionization potential of the atom, plus more or less 3 times this conservative energy, which is the mean kinetic energy that the electron acquires by oscillating in the field, in the laser field. So you can, by playing with the atom and with the intensity of the laser, you can extend this region quite a lot. You can go deep down into the deep ultraviolet or extreme or soft X-rays. So if you play with that, you can essentially cover all this region of spectrum with the laser harmonics. And this is a very nice and nice because it's a tabletop source, coherent source of radiation in a very difficult spectral region. So in this region, normally you don't have too much, especially when you go in this in the shorter wavelength regime. You have synchrotron radiation, which is not tabletop at all. And so this is, I mean, a very nice source. So you can use that for time-solved studies, but okay, the idea, when I started to work with this kind of sources, my idea was still to try to do spectroscopy that was coming from spectroscopy. So my idea was trying to use this kind of sources for spectroscopy. As I told you, short pulses are not good for spectroscopy because if you have a short pulse, frequency, it's the frequency width is the order of the inverse of time duration, so it can be very large. And if you want to measure a very narrow transition, atomic transition, it will be, I mean, it will be completely smeared out by the line width of the laser. Okay? So at first sight, you cannot use this kind of sources for high resolution spectroscopy. And this is what was generally what was the general idea at some years ago. Then you can do something else. For example, instead of using just a single pulse, you can use, for example, pairs of pulses delayed in time. So if you use 2 pulses delayed in time by, let's say, a larger delay, then the spectrum, corresponding spectrum, is no longer this broad one. It still has a broad envelope, but it's now modulated in a sinusoidal way, so that essentially the effective resolution is of the order of the inverse of this time delay. So if you make this time delay long enough, you can gain spectral resolution. So you can think of doing spectroscopy this way. And if you do this, maybe you can combine the, let's say, good points of using a pulse laser, which is high deep intensity, so you can use nonlinear processes, and you can also probably obtain high spectral resolution. So this idea is somewhat similar to what Norman Ramsey invented in 1950, and why he got the Nobel Prize in 1960, I guess. The idea was, at that time, they were doing microwave spectroscopy, and the spectral resolution was limited by the finite amount of time of interaction between the traveling atoms, because they were using the gas jet, and the regions where the microwave field was. So the idea of Ramsey was, instead of using just a single interaction region, use two interaction regions, which were placed, say, far apart, so that the atom interacted first with one and then with the other one. So that this way you could essentially effectively increase the interaction time, and which was not just limited to the crossing of this region, but was essentially the distance given by the time of flight between these two regions. So the idea that we were using similar. So instead of using just a single pulse, so a short interaction time with the atom, we can use two pulses related in time, which essentially virtually increase the interaction time by the distance between these two pulses. So the first attempt of doing this was done with the ultrashort pulses, then with the two-photon transition in cesium, and this was the start of my collaboration with Bellini in 1997. So okay, just quickly. So the idea is that this is a cesium cell. We have two-photon transition, and instead of using a single pulse to probe this transition, we use two pulses, which are generated by a microcentrifugometer, where you can delay the delay between we can change the delay between the two arms, so that we create two pulses delayed in time. So we can interrogate the atoms with this pair of pulses, and depending on the time difference between these two pulses, you see these Ramsey fringes. And by measuring this, and you can measure this over a long delay range, you can, for example, see this bit node, which is exactly the difference between the frequency of these two transitions. So with using a very short pulses, which are in principle not useful for spectroscopy, you can gain spectral resolution. So the idea, so we did this first, and then the idea was to apply this to high order harmonics, because in that case you can really gain much, because you can do spectroscopy in a region where there are no other, let's say, sources available. So the idea to move to perform Ramsey spectroscopy with harmonics could be the following: you start with a laser, pulse laser, you generate harmonics, so you start from the infrared, you go to the extreme ultraviolet, and then you use some microcentrifugometer again to split this pulse into two, which are delayed in time in a controlled way, and then do spectroscopy of sample. Unfortunately, I mean, you cannot do this in extreme ultraviolet because there are not good beam splitters. It's difficult to split or recombine a pulse in extreme ultraviolet. Now, some people are doing that with some particular spectral regions, but it's not easy at all. So one way to do that would be to reverse these two steps and start with a laser, then use a microcentrifugometer first, so start with create two pump pulses in the infrared, and then use these two pump pulses to generate high order harmonics, and hope that the, let's say, phase relationship between these pump pulses is preserved in the phase relationship between these two. And so when we started to do this kind of things, this was absolutely not even, I mean, people believed that this was not possible because harmonic generation is not a simple, let's say, nonlinear process. There are, let's say, some nonlinear phases involved and so on. So people believed that this was not possible. So we tried with a very simple experiment. So this is an old picture you see, and you can see from the grayness of the picture. And so the idea was to start from two coherent laser pulses, like the ones that you can generate by splitting a single pulse in a microcentrifugometer, then misaligning them a little bit and generate harmonics in two different points of the gas jet. So if the generation process preserves coherence, then we should be able to see interference fringes in the harmonic field. So this was the experiment. In principle, it's a very simple one, and we indeed saw very nice fringes. And so this was the start. This was the first demonstration that indeed, I mean, this high order harmonic process, generation process, can preserve coherence. It can be used for example, for many different things. For example, by looking at this, we could study the detailed, let's say, dynamics of the electrons which generate harmonics at the attosecond time scale. And for example, once you can do this, you can, for example, place a sample in one of the two beams and see a shift of the fringes. So this was the beginning of the application of harmonics to interferometry in the ultraviolet, which is important for plasma diagnostics and so on. And because its coherence is preserved, you can really use this kind of let's say scheme to perform a Ramsey spectroscopy with harmonics. And this is what we have been doing later. So this is a typical experiment that we are still doing now. And as I told you, it's a Ramsey spectroscopy with iron harmonics. So we start with pulses in the infrared. We have a microcentrometer in the infrared to split in time this pulse. So we generate two pulses delayed in time by a given delay. And then we generate harmonics in a gas jet. So we generate two pulses of extreme ultraviolet light that we use to probe an atomic sample. So in this case it's argon, and you see the first. This particular experiment, it's the ninth harmonic of an infrared laser, which is about 90 nanometers wavelength. So we have probed the transition with two pulses delayed in time. And depending on the delay between these two pulses, you can have either transfer all the excitation to the you can excite this upper level, or you can completely de-excite that and bring everything to the ground state. So changing the delay in this microcentrometer, we can see a variation in the population of this level, which is probed with another infrared photon which is coming this way. And so this is what we see, and these are the Ramsey fringes in the extreme ultraviolet. And now these are similar to what I showed you before for the cesium transition. But for the cesium transition, the period of those fringes was about optical period, something like 2 photon transition, so it was 1.3 femtosecond. In this case, we are probing with the extreme ultraviolet light, so the period of this transition is it's 290 attoseconds. So this is a very, let's say, difficult experiment, because we have to control, for example, the delay between these two pulses at the attosecond time scale, and but it works. And we can, you see, these fringes can be used to perform spectroscopy in the extreme ultraviolet with a resolution which is something like this, 10 to the 5th, which is So this spectral resolution essentially is the inverse of the maximum time delay between the pulses that we can use. If we have a microcentrometer to generate the delay between these two pulses, so this delay is given by twice the, let's say, displacement of one of the two mirror divided by the speed of light, and the resolving power, which is just the frequency divided by the line width, is just given by 2 times this mirror displacement divided by lambda. So if we have radiation, extreme ultraviolet radiation at 30 nanometer wavelengths, just 1.5 millimeters of mirror displacement, which is just very, very little, can give us 10 to the 5 resolving power, which is essentially the same as the state-of-the-art synchrotron monochromators at synchrotron sources. So with the very simple setup, tabletop laser source, and a small interferometer with a very small mirror movement, we can get the same spectral resolution that we can get with synchrotron radiation. Can we get even, let's say, higher spectral resolution by using this approach? So I'm showing you that even using very short pulses, so in pulse sources, we can do something that some years ago was only possible with the very well-stabilized laser, continuous wave lasers. Can we go even faster? So again, if you use a single pulse, you have a broad bandwidth in frequency. If you use 2 pulses, you have a still broad bandwidth, but you have a sinusoidal modulation with this inverse of the time delay period. If you use, instead of 2 pulses, you use a series of, let's say, many pulses, then what you get is, again, same broad bandwidth and the same spacing between these peaks, but now each peak is much better defined. So what you have essentially is a frequency combo, and this is what a mod-lock laser, a normal mod-lock laser emits. So you have a mod-lock laser emits a train of pulses in time, and its spectrum is something like this. So one can think that using a mod-lock laser and we can essentially generate a sort of a Euler of the frequencies that can be used to measure any other frequency in an absolute way. The problem is that all these peaks in frequency space are not simple multiples of the repetition rate of the laser, which would be what we want. In that case, I mean, you could just essentially count the spectral peaks to have a very precise and absolute measurement of the frequency of each one. Unfortunately, there is this additional term, which is called the offset frequency of the frequency comb, which is given by the fact that the pulses coming from the modular laser are not all identical to each other, but there may be a phase slippage. The envelope is always at the same, let's say, time delay, time distance one from the other. But under the envelope, there may be a phase shift of the field, and this phase shift is responsible for the fact that there is this additional frequency here, which shifts all this comb from the, let's say, from the precise multiples of the repetition frequency of the laser. So how can we measure and control this? This was, and the idea, this was essentially the idea to stabilize frequency combs that comes from that edge, was to, if you have a broad enough spectrum, what you can do is to take one of these lines here in the short frequency, low frequency side of the spectrum, and frequency double it in a crystal, for example, and mix it with another peak which is on the high frequency side of the spectrum. Then if you just pick the right lines of the comb, the difference between these two frequencies is exactly equal to this offset frequency here. So you can measure it and you can control it, and in the end you can have a very stable and absolute reference of frequency lines that you can use for metrology, spectroscopy, and so on. The problem is that if you want to do something like that, you need a comb, a spectrum of your modular laser, which is wide enough. It has to be at least 1 octave in frequency. So it must span a frequency and it's double. And when this idea came out, about 1997, it was not possible. I mean, the modular lasers that exist at that time were not giving such broad spectrum. So we needed some way to enlarge the spectrum, and the idea, one of the ideas, was to use supercontinuum generation. So supercontinuum generation is something that you always get when you have intense and short pulses, and you interact them with some, essentially any material. You have, besides the normal ring index of refraction, you have some nonlinear contribution to the index of refraction, which depends on the intensity of the laser field itself. And this gives a modulation of the phase of the field, and so a broadening of the spectrum. And this broadening can be so large that the pulse can become white, essentially white light. So this kind of process is common if you have a high enough intensity in the field, in the laser, and it's the result of many different processes. The main one is self-phase modulation, which is this one, but there are many other effects which make it very complicated. If one could use this kind of process to broaden the spectrum of the modular laser wide enough so that you have some essentially white light pulses, you could use a scheme like this. So you start from a modular laser with pulses which are very short, but not short enough that their spectrum is 1 octave broad. You can broaden them in this sort of in this nonlinear process, and then use this to apply the trick that I showed you before to measure the offset frequency of the laser and to have a real frequency comb. But the problem is that, okay, when this idea came out, supercontinuum was considered a very messy and incoherent process. So the general opinion was that this kind of process could not work for stabilizing modular lasers and generate frequency combs. Anyway, again, we try to do a very quick test if this was indeed the case. So this is, again, a very similar experiment to what I showed you before for high order harmonics. Again, instead of generating harmonics in a gas jet, we generated 2 pulses of supercontinuum in a piece of glass, or in this case it was calcium fluoride plate, and look for interference at the output. If the process was completely incoherent, as many people expected before, then we should wash out any kind of interference. And so, I mean, we didn't expect too much from this experiment, but we tried and we saw very nice, okay, these are very real, say, experimental fringes. So we saw very nice and stable white light interference fringes, which means that this nonlinear, extremely nonlinear process, extremely messy process, was indeed able to essentially preserve the memory of the phase of incoming pulses. And so it was possible to use this kind of process, so extreme broadening by supercontinuum generation to broaden the spectrum of a modular laser and then to stabilize it. So this was the start of a frequency comp based on this kind of a result. Ted Emshed won the Nobel Prize in Physics in 2005, and these are words. So, okay, yeah, this is a movie from the. This is the Nobel Prize ceremony in Stockholm in 2005, and okay, Ted Emshed is talking about the experiment that we did together in Florence, and is showing maybe. Okay, saying that it was too lazy at the time to take notes on a notebook, so it was using a camcorder. It was 1997, and it was okay. That's me somewhere, and it was using the first digital video camcorder that I had seen to take notes in the lab, and there is a recording. Yeah, okay. So these are the white light fringes. And so this was a very simple and successful experiment, and it was the start of, let's say, the application of very short, let's say, pulses, which at that moment had only been used for time-resolved spectroscopy, so for time-resolved investigations, to high-resolution spectroscopy in the frequency domain. So this was an example of, let's say, how mixing ideas from one field with another one, we can get some, let's say, new and interesting results. In 2005, there was another winner of the Nobel Prize. It was Roy Glauber. It was essentially the father of quantum optics, one of the fathers of quantum optics. And at that time, essentially in 2005, I had already started to move again from ultra high laser intensities, which was what I was doing before, to quantum optics, indeed. And so, again, there was another extreme change in my, let's say, scientific life. And, well, it's not really a change because I'm still doing both of the two things together. And extreme, let's say, extremely different regime from this kind of regime where you use very intense pulses, something like 10 to the 16 photons per pulse, and essentially a purely classical description because the fields are so intense that there is no, let's say, quantum effect there, to the single photon regime where you have pulses which contain exactly one single photon and where quantum effects are really important. And by the way, this is Roy Glauber and in our lab in which year, after the Nobel Prize. So, why is quantum optics important? Okay, and why we do it? We do it because it's fun, because it's and this is my main motivation, because it's really, let's say, nice to see some fundamental quantum mechanical objects and rules essentially that work in a lab. And for example, in the following years, we have been really working with some very basic ingredients of quantum mechanics, like creation and annihilation operators and computational relationships and so on. And so mean, this is what I like essentially of quantum optics, because you can really implement in a lab something that you always see in your, let's say, quantum courses, but you never, well, at least for me, I never understand them really. I just see them as a mathematical relationship and never understand really what they mean directly. And then it's also can also be useful, of course, because these quantum tools can be useful for new technologies, and for example, quantum computing, communication metrology, and some of these new technologies are already being implemented. For example, quantum cryptography is one of the examples where quantum advantages are already being used. And I don't know how many of you know about this, but okay, we'll just give a very short description. So suppose we want to send a secret message. The classical way of doing it, which is also a secure way of doing it, is to encrypt the message with a key and send it in a channel which can be insecure. It can be a public channel. And if the receiver has the same key, it can decrypt the message. And there are, let's say, rules to make sure that this transmission of messages is completely secure. And the key to the security is really the key. If you're able to share the key in a completely secure way, then you can exchange messages safely. The problem is to share the key. In fact, this is the main point of cryptography. And normally in classical, say, physics, key is a classical object. So it can be ink on a piece of paper, it can be a radio wave or a light pulse. And in principle, a classical object can be copied and without disturbing it. So the advantage of quantum cryptography is using a key which is made of quantum objects, which in principle, like a single photon, can only be measured once. So once they're measured, I mean, they cannot be reused essentially without disturbing them. So the idea is that you can use, for example, quantum objects like single photons to share a common key and then in an absolutely secure way. And this kind of idea is already being implemented in a commercial way. So how can you generate single photons, which are essentially the basis of this quantum optics stuff? Ideally, you would like to have a photon gun, something that you just push a button and emits a single photon on demand. Okay, you have millions of billions of photons emitted every second from a laser pointer, and can you just attenuate this kind of light by 10 to the minus 15 to get a single photon per at a time? Well, the problem is that you cannot do it, because if you have a coherent state, which is the quantum state of light emitted by a normal laser, if you attenuate a coherent state to the level of having on average one photon per, say, per pulse or per second, the photon number distribution is not fixed on one, but it has this kind of distribution, which means that about 40% of the time you have nothing, 40% of the time you have a single photon, but you have a significant probabilities of having two photons or more. And you don't want this, because if you have two photons, for example, you can a spy can just split, take one of the two photons and read the information without disturbing the other one. So ideally, you would like to have real single photons. You could attenuate even more, but if you attenuate even more, if you attenuate this one by 10 to the minus 16, so that on average you have 0.1 photon per second of pulse, depends on if you have a continuous wave laser or a pulsed one. If it's 0.1 on average, it means that most of the time, almost 90% of the time, it will be back where will be nothing. And only a few times it will be a single photon. And you don't know when a single photon is being emitted. So you don't want this kind of source. This kind of source is essentially useless. You want a real single photon source. And our way of generating single photons is by means of parametric time conversion. Spontaneous parametric time conversion. So this one works by nonlinear process, which is essentially the inverse of second harmonic generation, where in second harmonic generation you have two photons which essentially combine to give a single photon double frequency. in this case, you have the opposite process. You start from a high energy photon, and then you can split it into lower energy photons with a given low probability usually. And in this process, you conserve the momentum and the energy, so that whenever you see a photon in one of these two channels, you know for sure that there must have been another photon on the other side with a well-defined frequency and with a well-defined direction. So this is a good way it's not deterministic. You're not going to know in advance when a single photon will appear, but when you see a photon here, you know that the other photon is there for sure. So it's called a heralded single photon source. And the idea is by this heralding, this one is announcing the presence of this one. So essentially you can eliminate this zero, this vacuum component, and just take the good events, which are these ones. So you get this kind of sources. And okay, so I started to work with this kind of sources. And the first kind of experiments that I did when I started to work with quantum optics was something which was very similar to what I did before again. And as I told you, if you use a microsync interferometer to split a single pulse in two and give a given delay, the spectrum of this two-pulse sequence is a modulated one. So what we did several years ago, when we started to work with this kind of sources, was now to do a sort of non-local modulation of the pulses. So these two pulses are, these two, let's say, photons are coming out in different directions, and their frequencies are connected to each other by where some is given by the frequency of a palm photon. So if we put a microsync interferometer in one of them, what we see is that we see a modulation in the other. So we look at coincidences, and we have sort of non-local spectral modulation of our single photons. So this was, again, exactly the experiment that we had done before in different field, which was just translated in this kind of, in this new quantum optics context. And it was very interesting, and it gave a good interesting result. How do we generate single photons? So in a more realistic way, this is the scheme. So we have this non-lock laser. We have second harmonic generation, which converts these, let's say, infrared photons into ultraviolet ones. And then we have the opposite process here with this crystal, linear crystal, and we have these pairs of photons. One is going to this detector, and when this detector clicks, we know that another photon is traveling the other direction, and we can measure it. The way we measure it is by means of homodynamic detection, which means that we are mixing these pulses with another intense pulse coming from the laser, and we take the difference between the outputs of the beam splitter. And each time that we have a click in this detector, we perform one of these measurements, and so we collect many of these measurements, and each of these measurements is proportional to the amplitude of the field of this single photon. So after a while, we get this kind of distribution, which is essentially the distribution of an amplitude of a field of the single photon as a function of the phase, and the phase can be changed by changing the phase of this so-called Doppler oscillator. And we can use this kind of distribution to reconstruct Wigner functions. Okay, I'm not going to explain what a Wigner function is, but this is essentially the signature of a single photon, which has it's symmetrical around the origin of the phase space, which means that the single photon has no phase, has no defined phase. It has a well-defined energy, but a completely undefined phase, and it's negative in the origin, which means that this kind of function cannot be a description of a classical probability because it is negative, and so it's a real quantum state of light. For example, other classical states of light are like this. So this is the Wigner function for the vacuum state, and if you measure this, this is the result of homodynamic detection, and you see it's zero, so the field is essentially zero on average, but you have fluctuations, which is just the vacuum fluctuations of the field. And this is a coherent state, which is a most classical state of light, which
which is essentially an oscillating field now, which still has the same amount of noise. So we can modify the schema for generating single photons to add single photons to some state of light. So to implement this photon creation operator, for example. And this is a very simple scheme. Instead of just using spontaneous parametric conversion here, where we have vacuum going in, we can add some light at one of the inputs. And when this detector clicks now, what the result is that on the other side we have essentially the application of the photon creation operator to the initial state of light. So this is the kind of scheme that we can use. So we now inject the crystal with sunlight here, and whenever this one clicks, we have essentially applied the photon creation operator of the state of the input. So we can, for example, use this scheme to add a single photon to a coherent state, which is the most classical and wave-like state of light, which has a very, let's say, well-defined intensity and phase, and the Wigner function is always positive, and is displaced from the origin, which means that it has a phase. So, on the contrary, this is the Wigner function of the Fock state, which is invariant with phase invariant, which means that the single photon has an undefined phase, and it's negative here. So if you can add a single photon to a coherent state, you get something which is, which can inherit some of the properties of the parents. So it is phase dependent, like the initial coherent state, but it has negative values, which tells you that the state is purely non-classical. And by changing the amount of, say, the amplitude of the initial coherent state, you can change the say no-classical or say no-classical character of the final state. So this is the experiment that we did some time ago, and if you change the amplitude of this input state, coherent state here. So if we start from 0, so we start from vacuum here, we add a single photon and we get a single photon at the output. So essentially a particle state of light. Then we can increase a little bit the amplitude of this one. From very small amplitude, you already see a breaking in the symmetry of the final state, which means that the final state is acquiring phase already. And then if you increase the amplitude here and you add a single photon, finally, if you start from a say, intense enough coherent state and you add a single photon, it doesn't change much. You have almost a coherent state at the output here. So it can change in a continuous way the character of a final field for a particle to a wave, essentially. And this is from this kind of measurements you can extract the Wigner functions, and you really see that it's a continuous change of the character of the Wigner function from a particle to a wave in this case. We can also subtract single photons from state, and we can implement a photon annihilation operator, and we can do it with a beam splitter with a lower effectivity. And in this case, when we say click here, we know that we have subtracted the photon from the state. So this is the kind of scheme that we can get. And for example, you can use this kind of operation to test something that was the definition of coherent states given by Flower some years ago. So the fact that coherent states are eigenstates of the annihilation operator, so we can apply the annihilation operator to the coherent state and find that it doesn't change, or find that if we apply the annihilation operator to a thermal state, then in another counterintuitive way you can increase the mean number of photons in the final state. And okay, there is some. I'm going to skip these down. It's late. So after this, we had a lot of comments from the fact that, for example, we have these counterintuitive results that subtracting photons from a state, you can increase the mean number of photons in the state itself. So it was some serious one, and then some less serious. This is the National Research Council in Italy, and they gave this kind of title, like maybe you can understand it. It's confirmed that with photons, mathematics becomes an opinion, which is not such a serious comment from the National Research Council in Italy. And then this was taken by mathematics is really an opinion, and then people wrote all kinds of comments about this. And then you can do something else. So you can subtract single photon with the speed. You can add single photons with the paramedic conversion, and we can combine these two. For example, we can first add and then subtract. Or first subtract and then add. And if you do this and look on the same initial state, and you look at the results, for example, these are real experimental results. So these are quadrature distribution that you get from online detection. So if you look at these two final results are completely different from each other. So you, by doing this, you can immediately, let's say, verify, not demonstrate, verify that the creation and annihilation operators do not commute. Because if you apply them in inverse sequences, so in this case you apply A DAG, and in this case you apply A DAG A, they give different results, which directly tells you that A DAG, the commutator of A and A DAG is different from 0, which is again something that when I studied was just a mathematical formula. I didn't really think about it, what it really meant. But we could essentially really implement this kind of operation in the lab and test that this is different from 0, and okay, in another experiment we really tested that this is really 1. And the kind of experiments that we did was something like this. So we can combine different operations for stop already. Okay. So this is the photon annihilation, this is the photon creation, and this is another photon annihilation. So we can say perform measurements of the final state when two of these detectors click. If these two click together, first we have a subtraction of a single photon, and then we have an addition. So we have A DAG. And if these two click, then we have a reverse sequences of operations, and we can measure the final states and get the results that I showed you before. And this is to show you that reality is much different from what I showed you so far. It's much more complicated, and but it works. So I think this is more or less all that I wanted to say. And the main idea that I wanted to give is that the best results that I got so far in my career came from bringing new ideas into different contexts. So, so the final message is that extreme changes are good, because you learn something in one field and you bring it to a different field, and it can be something which is new and that can bring new interesting results. And we also used our laser, our ultrashort lasers, and our supercontinuum sources for performing optical brilliance tomography. And this is Nazionale, I don't know if you ever. It's okay. It's a famous painter, and this is something for 1476, before the discovery of America. And this painting was in our lab for 2 days, and we performed measurements there. And so it was. This is another kind of, let's say, extreme application of our light sources. So this is the end, and these are my main collaborators, and many others. And Katyusha from here, from CIFE, has been one of our recent collaborators. I've not shown any of the results that we got together. And so I want to thank you for your attention, and there may be PhD and postdoc positions available in Florence, so if you're interested, just contact me or Katyusha. And that's all. Thank you.
Proving that this higher harmonic generation is also in the end complementary, right? So nowadays it looks obvious it's complementary.
Yeah.
Why do people think that it's not complementary? What's the point of view that they had before? Why did they defend this?
It was because during this generation process there are also some nonlinear phase contributions, and they were thought to be, let's say, not so well controlled. There was some, essentially, this was based on sure the laser radiation which is in the harmonic radiation which is emitted, which depends on the trajectories of the electrons which generate harmonics themselves. And since there are different trajectories that contribute to the generation of the single harmonic, the idea was that these different trajectories were going to give some nonlinear phases which were not well controlled. Instead, with that kind of experiment, where we saw fringes in the harmonic conditions, we demonstrated that okay, that there are different, we can essentially differentiate the contributions of the different trajectories of the electrons which generate harmonics, even by just simple pinhole, for example, because they have different, let's say, spatial distributions. So in that case, you can just isolate a single harmonic trajectory contribution, so you can have a much more controlled, let's say, nonlinear phase and nonlinear shift. And so that was really useful. Anyway, well, also for supercontinuum, you can scroll down. There is no real reason why it should be incoherent. But people just thought that it was a completely messy process. It was just a sort of like. Sorry? Yeah, exactly. So that was the common idea, and no one tried to test it. Instead, because of, for example, for the supercontinuum, the fact that filamentation, for example, is a very stabilizing process. The fact that you have filamentation because of, let's say, self-focusing, and so it's an effect which essentially just clamps the intensity. So essentially, it just keeps the intensity stable during the generation, which helps in, let's say, stabilizing the process.
So the problem was actually the opposite. It's how to explain the lead state to the review.
Yeah, I don't care. It's weird, so let's do it now. Yeah.
I asked the same question that I asked you last time.
Yes. And I have the same slide there.
But I remember that you had some kind of intuitive explanation for the fact that by subtracting one photon from the state, it would increase the average number of photons.
You want to see?
Yes.
It's the same slide. I didn't show it. So it's this one. So the idea is that, okay, when we saw this effect that you subtract a single photon from a thermal state of light, we found that the final state had a mean photon number which was double than before. That was really strange. We thought it was just quantum magic. But it's not quantum magic, it's just it also happens in classical statistics. So the idea is that you start from an ensemble, you suppose you have a lot of heads with a distribution of rabbits inside, okay? And the average number of rabbits inside the head is this one, N0, okay? Then you take away the rabbit from the heads, and the final mean number of rabbits in the heads is larger than the initial one. How can it be? Okay, you don't need quantum rabbits, okay, for this. It also works with classical rabbits. It just depends on the probability distribution that you have, your initial probability distribution. If the probability distribution has a larger percentage of vector, so if many of your heads are initially empty, like in this case, suppose half of them are empty and half of them contain 10 rabbits. So on average, you have 5 rabbits per head. So if you take away rabbits, you can only take away rabbits from the ones which contain rabbits initially. If it's if it's empty, you cannot take a rabbit away. So if you select those heads where you were able to take a rabbit away, so the final distribution is that you will only have heads with 9 rabbits. The probability of having 0 rabbits inside the heads after you have subtracted them is 0. So the final mean number of rabbits in your, say, smaller sample is 9, which is almost double than the initial one. And this is not fun. This is just the fact that if you're able to subtract the rabbit from the hat, it means that there was a net, there was a rabbit initially. And so you're discarding all the hats which didn't contain rabbits. So if you start from a distribution which has a large vacuum component, then immediately you're able to subtract something. Immediately you have a larger number of particles or rabbits at the end. So this is a sort of trick, but this is.
Está vendo aí pelo eu vi que uma frase de 3 minutos. Uma frase de delezinho. Até que corrigir, né?
Ele está usando uma webcam, mas no início estava tudo certo. Tem um slide bom, um slide aí na hora H semana que vem melhor. Fecha para achar perdido.
Porque ele voltou uma reunião, aí eu
The problem is more than one desire. So you have
sample, okay.
Na verdade, você vai usar o seu pico para filtrar desse aí. Você tem dois trajetórios diferentes. Você faz a filtragem, elimina um e a outra você compreende.
No meu já tem instalado.
Isso já é imediato.
We also did experiments to really try to say
O programa que a gente faleceu foi.
Mas realmente o Marcel gostou. Marcel disse que ele ficou na brecha de propaganda. Eu expliquei o que é.
Porque ele é o gratuito.
Não, eu expliquei isso pra ele. Hey Marco, thank you very much.
Oh, thank you very much. I'm sorry, I don't know if it was
No problem. Actually, it was our first experiment.
So yeah, maybe you better try again with another.
I was receiving messages from everywhere.